Hello, you are listening to Pankaj Rai, and in this video we will be discussing the numericals of the chapter Electrostatics. We will be discussing electric field intensity around a sphere and a cylinder. So let us begin with a sphere. Now, consider a sphere of radius, let's say r, capital R. And let's say this sphere is completely charged and the total charge on the sphere is q. Okay, now let's say there is a point P which is at a distance of small r from the center of the sphere. So what is the electric field intensity at this point? It is given by the electric field intensity at a point which is at a distance of small r from the center of the circle, whose radius is capital R, and it is charged by charge q, is given by 1 by 4 pi epsilon times q by small r square, where epsilon is the permittivity of free space. We'll discuss about it in some time. Okay, so this is the formula. Now there are other variants of the formula as well. Okay, so let us discuss that. Now let us focus on the geometry of the sphere. The sphere is having a radius of r, so we can say that the area of the sphere is 4 pi r square. Okay, and the total charge on the sphere, we know that it is q. So total charge on the sphere is q. Now I want something which is called as surface charge density. We have surface charge density. Okay, it is denoted by letter sigma, and surface charge density is defined as total charge per unit area. So surface charge density, which is sigma, is total charge per unit area, so it will be q by 4 pi r square. So from this I can also say that q is equal to sigma times 4 pi r square. Okay, now let us substitute this q at this place. So we will get electric field intensity as 1 by 4 pi epsilon into q, we will substitute as sigma 4 pi capital R square and divided by, and there was small r square. Now 4 pi will get cancelled, and we will have the formula for electric field intensity as E equals to, will be having sigma by epsilon times capital R square by small r square. So this is another variant of electric field intensity at a point which is at a distance of small r from a charged sphere of radius capital R, where sigma is the surface charge density and epsilon is the permittivity of the medium. Also notice that if the point P is just outside the sphere, so this small r will be same as capital R. So small r will be same as capital R, it will get cancelled. So so electric field intensity just outside the sphere is electric field intensity just outside the sphere is given by sigma by epsilon. Okay, so these are the formula for electric field intensity around the sphere. There are two variants, one is this, other is this, and this is the formula when the point is just outside the sphere or just on the sphere. Okay, and electric field intensity inside the sphere would be 0. Now let us move ahead with the cylinder. Now consider a cylinder whose, let's say this is, let's say, let me draw the axis of the cylinder. So let's say that this is the axis of the cylinder, we can simply say that this part will be the radius of the cylinder. Let's say that this is the length of the cylinder, and let's say the cylinder is charged with a charge of q coulombs. Okay, now the question is, let's say there is a point which is at a distance of small r from the center of the sphere. So let's say there is a point, let's say it is here, this is a point P which is at a distance of, let's say, small r from the axis of the sphere. So what is the electric field intensity at this point? It is given by electric field intensity at a point outside the cylinder at a distance of r from the axis of cylinder whose radius is capital R, and the charge on the sphere is q, the length of the charge of the cylinder is q, and length of the cylinder is L. So it is given by 1 by 2 pi epsilon into, it will be q by L upon R. Okay, now what is this q by L? Q by L, you can think q is charge per unit length, so q by L is charge per unit length. Okay, so that is called as lambda, which is charge per unit length. So I can say that lambda, which is charge per unit length, is q by L, or I can also say that the charge is lambda L. Okay, so this formula can also be reiterated by removing q by L by lambda, which is charge per unit length. Now let us move ahead and look at the other variants of the electric field intensity in case of a cylinder. For that, we have to find the surface charge density, which is sigma of the cylinder. Surface charge density is the total charge per unit area. So total charge on the sphere is q, and the area, or the surface area of the sphere is 4 sorry it is I'm stuck. Surface area of the sphere is 2 pi rl, 2 pi rl, 2 pi r, which is the circumference, times the length, so that is the area of the cylinder. So sigma, which is surface charge density, is q by 2 pi rl. So I can say that q is sigma 2 pi rl, or I can say that q by L, which is charge per unit length, is sigma 2 pi r, and charge per unit length is also said to be lambda. So let me substitute this q by L by sigma 2 pi r. So what do we get? We get E is equal to 1 by 2 pi epsilon times, in place of q by L we can substitute either lambda, so it will become lambda by r, which is charge per unit length, and we can also replace by sigma 2 pi r. So let us replace by sigma 2 pi r. So it is sigma 2 pi r divided by small r. So 2 pi and 2 pi will get cancelled, and we will get electric field intensity as sigma by epsilon times capital R by small r. Okay, so this is another variant of electric field intensity at a point which is at a distance of small r from a cylinder whose radius is capital R. Okay, now obviously let's say if the point P is on the cylinder, so this small r will be equal to capital R, so they will get cancelled here. So electric field intensity just outside the cylinder is given by sigma by epsilon. So these are the variants for electric field intensity for a charged cylinder. Now to solve the numericals of this chapter or on these topics, you should also be aware of the units and the values of different terms. Okay, so let us begin. The E is the electric intensity, and electric intensity's unit is Newton per coulomb. Okay, or sometimes it is also volt per meter, but mostly it is Newton per coulomb. Okay, now next thing which we did was lambda. Lambda is the surface charge density. So surface charge density, let's say its unit will be surface charge density, which is charge per unit area. So charge is coulomb per unit area, so it is coulomb per meter square. Then we also did lambda. Lambda is charge per unit length, so it is charge per unit, let's say, length. So we have charge per unit length. So charge per unit length is coulomb per meter. Obviously you should know that Q is charge and the unit of charge is coulomb. Okay, now let us move ahead with epsilon. Now what is epsilon? Epsilon is permittivity of the given medium. Epsilon is the permittivity of medium. Now epsilon is mostly written as epsilon 0 k, where epsilon 0 is permittivity of free space. Epsilon 0 is permittivity of free space, and the value of epsilon 0 is given as 8.85 into 10 raised to minus 12 coulomb square per Newton meter square, or it is also farad per meter. Okay, and what is K? K is the relative permittivity, or it is also called as dielectric constant. It is either dielectric constant or relative permittivity, and you should know that for air K is equal to 1 for air. Okay, or vacuum you can say. It is unitless because it is as you can see, K is epsilon upon epsilon 0, so it is a ratio of two similar quantity, so it is unitless. You should also know one of the value of a term, which is 1 by 4 pi epsilon 0. The value of the term 1 by 4 pi epsilon 0 could be substituted directly as 9 into 10 raised to 9 Newton meter square per coulomb square. Okay, so you should be thorough with all these terms and their units and the values, and you should be remembering the variants of the formulae for a charged sphere and a charged cylinder. Then you can solve any numerical on these topics. For your information, I must tell you that you can try these numericals. The solved example 1 is based on the sphere, and solved example 2 is based on the cylinder, whereas problem for practice number 4 is based on this sphere, and problem for practice 5 is based on the cylinder. So you can try it by yourself, and you will get it. Thank you very much.